Say something.
Something.
Okay.
Something. That'd be a good opening.
That might be it.
You recorded it?
Mm-hmm.
Oh my God, no. Are we ready? I'm waiting on you.
I was waiting on you.
No, I'm waiting on you. I'm sitting over here just waiting on you. Like,
You said, hold on, I'm reading this text chain.
that was a long time ago.
I know, and you never said you were done.
Let's go.
And I know
Come
it's
on.
a long...
I'm ready to get this going.
Okay, well then let's go.
Read another message now.
What? Hi, everybody, and welcome to this week's episode of From Art to Atoms.
The Ultimate Curiosity Show.
I'm Brandon Shoemaker.
I'm Michael Fols.
And this week, we're talking about a topic...
Wait.
What?
Wait.
What?
I want to go ahead. Before we even dive into this week's topic, I want to go ahead and make a correction from last week's topic on serial killers.
Oh, okay.
Okay. So you mentioned that New Orleans had the Axe Killer of New Orleans or whatever it was. Is that what?
Axeman.
Axeman.
Yes.
Okay. And so I want to just go ahead and give a shout out to my emotional support coworker, Cassie. She came into my classroom on Friday or Thursday morning and said, "You really didn't know that there's a serial killer from New Orleans?" And I said, "Who knows this stuff?" And she said, "Well, I did." I said, "Well, how did you hear about it?" And she's like, "Well, I listened to the true crime podcast." And she said, one of the ones that I listened to did a whole podcast on him.
Mm-hmm.
And apparently this serial killer, as long as you played jazz music and he heard it, he did not come after you. So I've been playing jazz music for like the past 2 days now. But anyway, so again, apparently that's a real thing. I didn't realize that was a real thing. So
You do realize this was in the 1920s and he's long dead now.
you never know. They have copycats out there.
Or it could even be worse. It could be the ghost of the Axeman.
No, I don't believe in ghosts. We already know that. It's a copycatter.
I know, but I do. And so that's why it's even more fun for me.
Well, then you can go ahead and believe the ghost is coming to get you.
Yeah, no, I believe the ghost is coming to get you because you didn't know about him.
Oh, well, I'd rather have my chances with a man and a ghost. I can hurt a man. I can't hurt a ghost.
Exactly. That's why it makes it all the more terrifying.
It's not real. Anyway, the Axeman apparently is a thing that people do know about. Just not this New Orleanian. Or Aunt Jean. She didn't know that either. So.
Or your mom.
And I was going to say, Mom called back later and said, "I didn't know that either." So I guarantee you, my family's just ignorant.
But
on New Orleans culture.
But what did Aunt Jean say to you by the end of the podcast?
What?
She had already researched it all and knew everything about it.
And she was going to go ahead and drill Uncle Brett about it to see if he knew anything about it too, which I have to follow up with that and see how that even went.
Yeah, no, that's what I want. I want to know if Brett knew about it.
Probably not. Anyway, so this week's topic.
Hold on. Now I'm taking back over.
Okay.
This week's topic is one that I have. So when I first conceived this podcast as an idea, I was driving to a competition. I had to drive the truck that had all of our sets on it and everything like that. And so I was riding by myself on this 5-hour trip. And so it was incredibly boring. Meanwhile, all the kids are on a school bus just having the best time of their lives. And I had to think of stuff to keep myself awake.
Burns.
Huh?
Burns is on that school bus too.
I know, and that's Kinsey, and so she was having more fun than I was, though.
Right, that's what I'm saying. She was on the school bus having the best time of their lives, also.
Exactly.
While you were trying to keep up with Hannah in the school bus.
Yeah,
he was
pedal to the metal.
He's like, that idol does not have a limit on it.
So anyway, I was trying to think of things to keep myself awake, to think about. And so I finally started thinking about, okay, what are all the different topics I would want to discuss on my podcast? And so this was before I talked Michael into being my co-host. And so the very first topic that I thought of and said, of course I want to talk about this, is tonight's topic. And that is string theory.
And to be fair, he wanted to do this topic
since day one.
I was gonna say in the very first 3 episodes of
Yeah.
the show, and I was like, dude, I can't. We don't know enough about this, and
He was even saying that as of this morning.
Yeah, I was like, I can't wrap my mind around this stuff. Just the name string theory intimidates me. It does.
And now, to the folks out there who have no clue whatsoever what string theory is, it is the realm of study of some pretty well-known and preeminent physicists out there in the world, the likes of Michio Kaku, who most people don't even know his name, and they just know as, the gray-headed Asian guy who talks like really intelligent people on all the science documentaries. So to talk about string theory, we have to talk about the world of physics. And most of us understand physics from just what we learned or maybe tried to learn or slept through in high school about it, and that's usually the Newtonian side of physics. We know that Sir Isaac Newton came up with all these laws of motion and things like that. And
yeah, I will say that, like, going through what my notes are about it, that seems to be kind of like the Albert Einstein version of physics, where it's very traditionalist and very what's the word I'm looking for, very concrete.
Yeah.
Does that make sense?
Yeah.
Like
observable.
Yes. This happens and this is how it is, not, and so we'll get into that, but it was very just kind of like concrete.
Yeah. And then and it was because of Einstein that they realized that Newton's laws didn't fully satisfy everything that was going on in science, in nature, in the universe for that matter. And it was all basically because of gravity. Gravity was sort of like the problem child. And so physicists realized that they had to delve deeper into their understanding of the physical world to understand how things were happening at the smaller level, which is what we call the quantum level. And that's the subatomic level. We know, in high school, you traditionally learn that atoms are the fundamental building block of nature, but that's really not true at all. Because
I wouldn't even say nature, I'd say the universe.
Okay, well, yeah, the atoms are the fundamental building block of the universe, but that's not true, because atoms are built up of subatomic particles.
Well, okay.
Yeah.
We knew that, though. In high school, we knew that those subatomic particles consisted of protons, neutrons, electrons.
Yeah.
And that's in our high school. We're talking 25 years ago. But,
right.
And I would say in the last 15, maybe 20 years, that's changed, because now we've discovered with advanced technologies that we now have subatomic particles.
Do they teach those in high school, though, is what I'm asking.
I did when we teach chemistry. I don't know if everyone else does, but I do mention, I don't teach it like per se that this is what it is. I do mention it that we now have technology that allows us to see further below that level of subatomic to where we can tell what a proton's made of now.
Well, and you say you bring up a good point there when you talk chemistry, because as far as chemistry goes, to study chemistry, you just need to know atoms and their subatomic particles. So,
well, no, you have to know how they behave also.
Well, yeah, that's true.
Like,
but
when we talk about electron spin, you have to know that. We teach that through electron orbitals.
Yeah.
That spin plays a part in how chemicals behave.
Yeah.
React together.
That's right. But for the most part, delving into these particles like quarks and bosons and photons isn't explored unless you're studying physics.
I would say even advanced physics, because we took physics in high school.
I didn't take physics.
I took physics in high school, and I just remember like what you said. I remember the gravity, those forces,
Newton's laws,
right?
Yeah,
how things, centripetal force works on that. All that. We didn't really dive into the quantum or that aspect of physics.
Well, because I think the reason for that is because it's incredibly advanced. Spoiler alert: we are by no means going to be delving deep into quantum mechanics or string theory for that matter today.
Our brains can't handle that.
Yeah, we're going to be talking on a very superficial level, and really just from an aspect, for me at least, of why it fascinates me the way it does. But yeah, I think we don't study that because it is so advanced, and simply for the fact of it's still debated. It's not, it's not a
law. It's a
It's not even well, I mean, string theory is
a
a theory.
Yeah,
but
it's not a law though, right?
Yeah.
And I think at that level too, even in high school, I mean, you're looking at master level work in physics here.
Mm-hmm.
Like you have to be at 23, 24. Your brain has to be fully developed. But 17 years old, I couldn't understand this stuff.
Which
I'm 44 now. On to be 45 in 4 months. And this morning, you heard me. My brain, I couldn't.
He literally called me this morning and said, I can't. What? What? It does what?
It is what it is. But look, so I'm serious. And I'll tell you, this is the part that got me, that it's scary.
Yeah.
This scares me because when you think about the magnification of really what this is, and I can only imagine blowing the mind of a 17-year-old with that fear of, oh my God, like it's.
Oh, but it's just like but I do it all the time when we talk about, we'll start talking about what is the nature of reality. How do you know that what you're observing is real? How do you know that what you can only observe out of your own two eyes and your two ears and so on and so forth? How do you know that what you're experiencing right now is reality? How do you know that you're not secretly in a padded room somewhere just going crazy?
Okay,
and it just blows their mind.
That's fine. I just want them to realize that a pencil's made of something. I need you to bring it every day.
So, that's really the aspect that the part that freaks you out, I'm willing to bet, is the part that I find beautiful about this theory.
We'll get there.
So yeah. Let's back up and take it kind of slow.
Do you want to do right now like a basic science lesson of what we're talking about, and just kind of refresh everyone of these subatomic particles and what they do and how they're formed and stuff?
Yeah. Take us there, Mr. Wizard.
I was going to say he's got hair, but I don't now. Anyway, okay, so look. So, we exist. We're made of, I'm going to say we're made of atoms, but after researching, I'm not sure that we are anymore.
Well, okay. Let's back up and before we even dive into that, let's just state what at the most basic level what string theory says.
Okay, go.
So string theory says that at its most fundamental state, everything in nature, everything in the universe for that matter, exists made up of not point particles, but these tiny little strings of energy, not matter even, but they are energy. And it's their vibration, just like the vibrations on a guitar or a guitar string or a violin string or something like that, that create these different sounds. The vibrations of these tiny little strings are what make all the different particles what they are. So at our core, at our most basic level, we're not even made of matter, we're made of energy.
I wasn't going to go there.
You weren't? You were holding your head like it was about to pop off, so
that's not okay.
What did you think I was going to say?
No, I'm just saying I learned a little bit more about it, I guess.
Yeah.
Talking about waves and stuff like that.
Yeah, I figured we wouldn't go into the full depth of it.
We are.
Okay.
We are. I mean, I think I can boil it down to the simplest terms of that and not get so deep into it, but I think we can give a little bit more than just... Because what you're describing to me, I don't have enough information to visualize. Because, again, that's another reason why it's very difficult. It's a conceptual thing.
Yeah.
You have to be able to see this in your head. Because
you
no
can't,
way you're seeing this.
There's no observation.
Right. And so you have to be able to kind of observe it in your head and conceptualize it. So when you explain it like that, that does nothing for me. Because even when...
Oh, really?
Even when...
Michio Kaku.
Yes. Even when he was explaining to me, like I watched like a 3-minute clip, for like string theory for dummies kind of thing,
Yeah.
And he was explaining it. And he had this like, I don't want to say plastic rubber maybe,
Yeah.
It just kind of looked like it was like a string. Like
yeah.
And he was moving around. He says, and so this... He said electrons can move one way and then they can move another way. And I was like, dude, you done lost me. You lost me. So I did. I found a documentary this morning to be freshed up on this because, I'm all about some documentaries. And I figured, I was like, there has to be at least one of them out there. And I was able to find one on Amazon.
Which one did you find?
It's a Nova special called String Theory of Everything.
Is it the one with Brian Greene?
Yes.
Yeah.
Yes.
Yeah,
And it's a
yeah.
couple of years old. Maybe.
Couple years. I think it was from the
20.
late 90s.
Yeah. And so things might have changed, but I got the basic foundation of it.
No, so what you saw was what I first saw about string theory that blew my mind and made me fall in love with it. So that's a good one to watch.
At least we're on the same page there.
Yeah.
I don't want to advance into any more after this. I don't want to learn more about this. I would just want to live my life and know that it is where it is. Because I don't want to realize that the Matrix really is happening and the universe is the playfield of it, I just want to keep my little simple life. Let me just collect my comic books and action figures and love my husband and dogs and go about my business.
Okay, well that's going to come into play in my final thoughts, but go ahead.
Okay. So and this is part of quantum mechanics. That's really where we boil this stuff down to. And there are particle laws. Particles behave certain ways. And
quantum mechanics talks about describing the universe at the subatomic level.
Right. So we're going down to the smallest of scales at this point. Okay. So, an atom consists of a couple of subatomic particles. There's a nucleus, which is kind of at the core. And then that's made up of positive charged protons and neutral neutrons, right? Then you have electrons, which are negative charged, spinning in orbits around the proton. And the electrons vary depending on what elements out there, what the atom's made of and stuff. And each element has a different number of electrons and protons, and you have a different number of electrons, different versions of that, isotopes and stuff like that. So we have all of this changing.
Yeah.
Okay. Basically, the protons spin, they vibrate, but the electrons are really the ones who are the fast movers. They, like everything else in the universe, does not like to be tied down, or what we thought used to be one path around the nucleus is not one path. And so this electron spins, and when we teach it just like the solar system.
Yeah.
So the sun is rotating and the planets are rotating around the sun, but the planets are also rotating on their own. Right.
Yeah.
So the planets are spinning and they are revolving around the sun on a path. And so it's kind of like a constant spin of everything spinning around, And so the electrons are spinning in the same way that the Earth is around as it follows its revolving path around its revolution around the sun.
Yeah.
Okay. And so what they were talking about, though, is spin of electrons. Electrons have different patterns of spin, and they go in different directions based on where they're located at on the atom itself. Okay. And so this is and again, this is where you look at classical views of this kind of stuff. That we thought that basically it had one path to follow, the electron. When we teach it again, we teach it that the electron is like a solar system. It goes around the nucleus in one path, which we now know is very not the case.
Yep.
And so we looked at how things behaved.
Yeah.
Okay. And just about 100 years ago, they're looking at how light behaves, right? And this is where I think this is where the quantum and all these theoretical theories really started kind of happening, and people were starting to have ideas on it. And this is kind of the birth of that, is that they were really looking at light.
Yeah.
And we know that light is a wave. It happens wavelengths, and we have all that, right?
Or is it?
Nah, anyway. But 100 years ago, you're looking at how light behaves. And so what they would do is they'd take a tube of heated gas, right? And they would look at it through a prism. And usually when you look at light through a prism, what happens is the light scatters.
Yeah.
Correct? And so when you have this heated gas, though, and you're looking at it through a prism, what ended up happening was that the light didn't scatter. It actually formed very specific lines of color.
Yeah.
And that wasn't what they expected to see. You have these scientists like Niels Bohr, who really, we teach him as the person who discovered this electron model and kind of what it looks like around. We still teach the Bohr model of when we draw atoms, we teach that, you know, how it looks around in the orbitals.
Now, when you talk about, are you talking about the concept of an electron shell?
Yes.
Or yes,
So,
okay.
yeah, we have to, when we talk about atomic theory, he's the guy we talk about that does that. Okay, we figured out that the nucleus is in the middle, electrons around it, and they're on different levels.
Yeah.
Different orbits based on energy. And so his electron cloud model, he discovered that, and didn't discover, but he came up with the theory that basically these electrons are on a fixed orbit around the nucleus. And unlike the planets, which are orbital and move and stuff like that, their orbits are semi-fixed, like they still fluctuate a little bit, but these electrons don't. And so when heated, the electrons would leap up and down orbits. When they would give off energy, they would jump down.
Yeah.
And when they would take in energy, they jump up.
Yeah.
Okay. And the thing is that this is where it started kind of getting really weird for me. You know where I'm going with this?
Teleportation?
Yes.
Yeah.
Because really, when we see things move, like, okay, if I'm in 4 lanes of traffic, right?
Mm-hmm.
And I'm watching cars go by. And when a car has to get from all the way in the left-hand lane to the right-hand lane to get off the interstate, we see the transition from one lane all the way over to the next all far right lane to get off.
We see it occupy multiple points in space between...
Right. We see the transition between point A and point B.
Right.
With this electron stuff, though, man, I'm going to tell you, this does not happen.
Yeah.
Because it basically is in point A and then instantaneously in point B.
Yeah.
There is no transition between the two.
Yeah.
And these electrons do this. They don't, when they move levels, we call it jumping levels, and that is literally what they're doing. They are in one point and then move to the next level.
Yeah.
Up or down around the shell. Okay. And so, like, to give an example, that's like, so basically saying like Mars is in orbit around the sun, but let's say that Mars just was like, okay, I'm going to pop from my orbit into Earth's orbit instead.
Mm-hmm.
And it's instantaneously there.
Yeah.
And not even that it just stays there, but it keeps on jumping back and forth between different orbits.
Yeah.
And that's what these electrons are doing. And thus the term quantum leap comes about. And that's where this is coming from. They pop from one orbit to the next.
Yeah.
They're either, the electrons on the atom are either here or there, but they're nowhere in between.
Yeah.
And so I'm like, okay, I'm watching this and I'm like, I mean, I can dig it. I got it. But
it boggles the mind of how that can be.
Yes. Like, and I can imagine like 17, 18-year-old me going, oh my God, what in the world? And then, like you said, the first thing that came to my mind was
teleportation.
Yeah, Star Trek.
Yeah.
Let's transport these guys out of here.
Well, and that's exactly, well, and okay, the reason why that fascinates us is because we do that with science and with technology. We look to the very small and then enlarge it and apply it to our scale. That's how we have, I mean, we literally have quantum computers that work on this infinitesimally small scale that are able to reproduce things at the macro level, let's say, that previously could only happen at the micro level or the quantum level, which is, micro level is still something observable. The quantum level is so small that we can't see it. And so, that fascination, the bizarrity of it all, obviously in the late 90s, in, my late teen years, of course, I fell in love with string theory and said, oh, this is the coolest thing ever. And so here we are.
Because you're weird like that. I'm going to tell you what, I couldn't.
Really?
Not at that age.
Well, but I mean, okay. But I mean, okay. So let me say first, I love the fact that, as you say, at almost 45 years old, you are still able to have your mind boggled by science, though.
Well, yeah, that's why I appreciate it. That's what my interest, that's one of the reasons why I teach it, because it never stops.
Exactly.
There's always something to explore.
Yeah.
So, yeah, of course, that's like.
Well, then, so let's talk about why it freaks you out.
Well, I'm not even there yet. We still got more to go.
Oh, okay. Sorry. We'll go where were you?
So, I mean, let's just look at like how they even figured all this out.
Yeah.
Like the history behind it. So when Bohr started saying all this, and this is probably the early 1920s, I guess. You know, that atomic age, I guess, when we're talking about this kind of stuff. So they did an experiment called the double slit experiment.
Yeah.
And so what this experiment did was basically they shot electrons out, right, through two slits.
Yeah.
Going through the slits, you would expect to see exactly behind where the two. So, okay. So it's like, I'm going to simplify it. Cardboard box, and you cut two small rectangular slits in the base of the box. So it kind of makes like a wall with two holes in it. And they're going to shoot stuff through the holes, right? And some are going to go through and some are not. Some are going to bounce back, obviously. Yeah. And so what they're doing is they're going to shoot, I guess, like a ball. We're going to just kind of take it like a marble and shoot a marble through the hole in the ball. You would expect that if they go through the slit, that the marble is going to basically make an indentation through the exact back of, whatever that slit is.
Yeah.
That's not what they found.
No. In other words, you would think that they would hit in a predictable pattern.
Right. Well, it wasn't so much predictable as it was a probable kind of thing.
Yeah.
And so the electrons were hitting this, I guess, a sheet, a foil sheet, making indentations in it. And they were able to see kind of where they lined up and where they fall. And of course, the middle is going to have the most probable. That's kind of where they find them, But this is where the lines were coming from of the light when that gas tube was looking through the prism. That's where these lines were being made, because the electrons, the way they were behaving was that the size of the wave at any location on the whatever they shot it at was the probability. So the bigger the size of the wave, the bigger probability that's where the electrons were found at. And again, it's not that that's where they were because they couldn't say for certain. It was just where we think they're going to fall kind of thing. So the larger wave doesn't mean that there are more electrons. It just means that they were more likely to be found there. So they're trying to like locate where they were being found at when they scattered the light. Part of the problem is that, and this is where Einstein comes in at, he couldn't accept this. He could not accept that probability was how the universe was being ruled by, not certainty. He didn't want to live in a world where, okay, look, I can't live in this universe that's being ruled by chance.
Yeah.
Like, I need certainties. Like the rule of gravity, the law of gravity, that's a certainty. It's going to happen. It's going to fall no matter what. Like, he needed the definites. And I think that's where Einstein had a lot of issues. Like, and he was quoted, God does not roll dice.
Yeah. God does not play dice with the universe.
Right. And Bohr's response was, stop telling God what to do. Like, who are you to say what God's doing? And so this is where part of the issue comes in at that the act of measurement is what forces the particle to make the choice in where it's at. So when we're looking at this, and this is where Brandon's talking about, because this is, I think, what he gets excited about or whatever, is that the electron itself is in one place at one time, but you don't know what place it's in until you observe it in that place.
Yes.
And
so
there, by doing that observation, you've now changed everything about it.
Yeah. The act of observing the phenomenon changes it.
Right.
Yeah.
And so that's where Bohr and Einstein were at conflict.
Yeah.
And
that was known as the Heisenberg uncertainty principle.
Right. Still is,
Yeah.
And so Einstein was like, okay, look, so this is like 1935, so we're beyond a little bit and more.
Yeah.
But Einstein's like, look, quantum mechanics, this whole theory stuff, okay, I can respect the observation. Like, and they did test after test after test, and every time they did this, it came out exactly the same way every single time. So they're like, okay, this is a large amount of data that's given us answers repeatedly. Like, it has yet to be proven, disproven. And Einstein's like, okay, look, I got that. But something's missing. Okay. And this is where my mind starts getting I'm about to start talking entanglement.
Oh, yeah.
This is where my mind starts getting kind of crazy. So Albert Einstein's like, okay, look, so I think that things in the universe, well, Bohr's really like things are connected. Einstein comes up with, there's an entanglement thing there. And so Bohr's like, okay, so let's talk about this. So the theory on entanglement is that, and to prove that quantum mechanics and quantum theory is incomplete, is that this whole entanglement thing is there.
Yeah.
Okay. And Einstein went to his grave not knowing, not believing in it, you know? But basically, so two particles can become entangled if they're close together. And when they're close together, their properties are linked. What I mean by that is I want you to take two marbles and I want you to spin them in an orbit. If they're close together, those two marbles will develop some kind of a string link between the two of them. And they're linked at that point. You cannot see it, kind of thing. You can't feel it, but they are linked in once they're in the same property wise, they become what they called entangled. Okay.
Yeah.
And even if we separate these two marbles
by light years,
yes, these two things, according to Bohr, are still linked. Okay. And so Einstein's like, this is the spooky action.
Yeah.
Yeah. He called it spooky.
Yeah. Literally.
Yeah. So basically, it's like electron spin. Let me bring it back to the particle. So if we have our electrons and we're spinning, and I think of like a roulette wheel. Like I'm gonna use the example they said in the show, like roulette wheel, right? And you spin it. You have basically a green and a red space, and you spin one wheel. It's gonna land on either green or red.
Black or red, but yeah.
Well, whatever.
Okay.
It's gonna land on one of the two colors. And the other wheel next to it, as long as they are linked, if one lands on green, the other's going to land on red. Does that make sense?
Yeah.
So no matter how you spin it, let's say that the one wheel you spin that one on and it lands on red, the other one by default is always going to land on green. And so because they're linked, that's how these particles are acting and behaving. Okay. So with electron spin, if one is spinning counterclockwise, then the other one by default is spinning clockwise.
Right.
Okay. And that would happen if they're right next to each other, or if we put one wheel on the moon and spun one on Earth, the other one we know without even looking on the moon, we know by default which one is going to be on the moon because of this
entanglement.
Okay. And so Einstein was like, I don't like the fact that these things are being connected. Like there's no way in the universe, no matter, like you said, light years distance, we're still kind of, there's a thread connecting us, right?
Yeah.
And so he didn't like this because when you make a measurement of one particle, you're basically affecting the state of the other particle. It's like what you said.
Yeah.
When you see one, just the fact of making an observation on it changes by default the other thing.
Yeah.
Okay. So Einstein's like, okay, look, we're going to challenge this. So Einstein's kind of take on this was that, okay, and I'm going to use again the example of what they used in the show when I was watching because it makes sense to me this way. Einstein basically is saying that the electron's destiny is already set in place before you make the observation, and it's not based on what you observe.
Right.
Okay. And so they say basically, okay, so think of a pair of gloves, a left and a right. If we take a left glove and a right glove and we put both of those in separate cases and transport those cases far apart, one on East Coast, one on West Coast.
Yeah.
If I open up the one that is on the East Coast and see the left glove in there, I know by default the one that's in the other case is going to be the right glove.
Right.
So again, Einstein's thinking, okay, so these things are basically like, this is already set in motion. It's not a matter of you seeing it. It's that. So the question was then, how do you measure what Einstein is saying? And so they were like, measure it. That's what Einstein's response was. Measure it. And so Bohr says that the act of measuring is what brought the spin to the definite state to begin with.
Yeah.
And Einstein says, no, you can't. It's already set in motion. You're just watching the reaction or the result of that motion that was set in place a long time ago.
Yeah.
And so again, Einstein went to his grave never conceding this.
Yeah.
And so this is one reason why the debate is still there, but there's no way, because we're talking about such a small scale, there's no way to actually solve it.
Yeah, because we can't observe it.
Quantums became a philosophical thing as opposed to an actual science. Okay. So advanced 30 years, right? We're in the 60s now.
Yeah.
We have better technologies.
Yeah.
And we're now shooting electrons and doing, atomic experimentation and stuff like that. So
were we colliding atoms yet?
yeah, I think we're in
particles?
the 60s. Yeah, we're in the 60s. So the thing though is like 1960, so John Bell is another physicist. He was a grad student at this point, and he was like, okay, look, I'm going to go ahead and try to figure this one out. I want to see if entanglement's real. So he's going to build a machine that will help determine the spin results of shared electrons in orbit. So he built a machine that lets us now see this. He measures the spin. So what they do with that, though, is that every result they got for every counterclockwise spin, there ended up being a clockwise spin. And so he was like, entanglement is real because we can measure the spin of these electrons and it's an equal number.
Yeah.
Meaning that, again, just like with DNA, for every A, there's a T. For every C, there's a G.
Yeah.
For every one spin in one direction for the one electron, there's another one on the opposite end of that one that spins on the other end. So they now believe, again, that entanglement is a real thing. We have evidence to show us that entanglement, these particles are connected somehow. So here's where my mind gets blown. We're talking about modern experiments. And I say modern like in the last 30 years experiments, 20 years maybe. So it goes back to what you were talking about as far as teleportation and transportation, like the electrons do through the shells, you know?
Yeah.
So Anton Zellinger did an experiment off the Canary Islands. And I think it's funny because they talked to him and was like, why the Canary Islands? And he's like, well, for number one, there's 2 observatories up here. And number 2, the weather's just nice, you know? So he's like that kind of guy. But what he does is, so they basically, on 2 different islands, they're about 90 miles apart, I guess, 90 miles apart, in La Palma Island, and then Tenerife is another island, I guess. That's the other one. So what he does is he basically creates 2 electrons, puts them together, or he's using light, so he's using photons, entangles the 2 that are generated on La Palma Island, and puts them together. And then through a laser shoots one of those electrons to the other island. And they then take another, that's electron again, photon. Yeah. They then take another photon on the original island where that one, the one of them is, and basically kind of connect it to that one also, while it's still shooting the other photon across to the island. And what they find out is that that third photon entangled with the one on one island becomes entangled with the other one, and then the other one becomes the third photon. So they're actually transporting the third photon into the place of the original one, right, on the other island 90 miles away. And so they've done this over and over and over again. And they're teleporting these photons 90 miles, showing that connection there, that string is still connected. And so this is where my mind gets blown. Okay. So on Star Trek, right? They and look, I mad respect for Bones McCoy, man. I am not getting on this transporter at all. I will take a shuttlecraft to the day that I die on this one. And this is where I called Brandon. Like, I remember we were getting ready for book club this morning. I think it was by 11 o'clock, I guess. Yeah. And I called him. I said, look, I can't do this. I can't. I said, so you mean to tell me that on Star Trek, when they use the transporter, that's not their original atoms anymore? Like, it's not. Because when you think about it, the original atoms are on, let's say that you're transporting from the ship to a planet, right? Yeah. The original atoms are basically transported, are destroyed. They basically take an image of the molecule setup of the person on the ship in the transporter, and then basically shoot their atoms to wherever the destination is. Using the atoms that are already on the planet, they then reconstitute in the exact arrangement that the ones on the ship were. And by default, the ones that are on the ship are now turned into something else. Yeah. Basically air. You know, they're just back into the universe. So when you're teleported or transported, you're no longer the original what you were born as. Yeah. As far as molecules, you are no longer the original molecules of your body. Yeah. Which, if you think about it, though, because
we never are anyway. We exchange atoms constantly.
Right. We are always losing and gaining and building and breaking down.
So does it really matter if we're the same atoms or not?
I get that. I get that. But that's where I said it's scary, because when you think about, okay, I can think about that. Yeah. I can think that my body is not what it was because 20 years ago, number one, I'm older. I've lost my skin has been completely replenished times over. My bones have broken down and built back up based on calcium levels in my body. Yeah. You know, I can think of that, and I'm okay with that because I'm still me. There was never an instantaneous moment where I lost everything and then became something else, you know? Yeah. But man, when you think about this, it's scary to think that we can visualize this. And I think part of the fear is that it makes you think about the universe in itself as a whole, as opposed to me. And what I mean by that, it makes me feel very small in the universe.
Yeah.
And I think that's fearful for a lot of people. And, like they said in the show, it's like, you're not fearful because we've already been replaced already. But they said, like, the particles don't make the person. What makes the person is the information they're made of.
Yeah.
And because that's sent identically from one place to the next, there's no fear there. But I think it's a psychological fear of having our atoms broken down and then reconstituted somewhere else. And that's where the fear is.
Well, and then it does get in, and that's where you can go into the philosophical level of it, of, if those atoms are destroyed in the, in the pre-transportation model, do you die and then you just have no memory of it because it happened with different atoms and with different particles?
I don't know.
Or it's almost like, I mean, we haven't talked about the multiverse aspect of string theory yet, but it almost begs the question of, well, is that just a division of realities and such? So,
I mean, and I'll tell you, like, comic books are built on multiverses.
Yeah.
So I'm very well versed in that. We know that, like, DC, there's 52 different universes. And that's, well, there isn't anymore. They got destroyed again. Anyway, every couple of years they rebrand it. They have to restart the universe because they need new readership. And, it's like, oh, here's the new universe. So anyway, there's now one, but anyway. But they.
Oh yeah, we need to press pause and back up. Yeah, under string theory, there is the requirement of the multiverse. That's a real thing. Just wanted to put that out there because we didn't explicitly state it.
And the multiverse is all based on different vibrational patterns. Also, like each multiverse has a distinct vibrational pattern to it. And in every sci-fi thing, comic book thing that I've ever, even like the mirror universe has a different vibrational. Those, or people come from the mirror universe in Star Trek have different vibrations. And that's how they can kind of tell who's there and who's not there. Based on the vibrations. Anyway, but for a while it took me really, as a kid, I didn't understand why the X-Men had so many different titles and so many different versions of different stuff going on, different teams and stuff like that. And I think that's one reason why I kind of was steered to DC, because DC was like, okay, look, here's our universe. And DC kind of reconstituted all that in the early 80s. And so as a comic book reader coming in the early 90s, late 80s, to my 10-year-old brain, that's easy to comprehend. Batman and Superman live on the same world. All these X-Men, I can't. But now I can as an adult. I can get that one comic, Elseworlds, Batman's different. And so he looks different in this comic book than he does in this comic book because there are different versions of him living and stuff like that. And same thing with the X-Men. There's different versions of them, and I get that now. But man, that multiple reality stuff and different dimensions, I couldn't understand that back then. Appreciate it now.
Especially when you realize that that's the actual nature of the universe according to string theory.
Yep. So hopefully Michael Fole's somewhere else out there in the world. I hope you're making a lot of money. Make that money, baby.
In that universe, this podcast is much more popular.
Yes. But that's, like I said, that's the fear of some, and that's, I guess, part of when I called Brandon, I was like, oh Lord, that terrifies me, that, my body being lost to the atoms. And like the guy said, what happens if there's a malfunction? What happens if the information is not the same? And we've seen that on Star Trek. In the very first movie, motion picture.
They address that.
Right. When you have the new science officer come on board and he's teleporting over and there's a malfunction between the space station and the Enterprise. And those two that were transported aboard, like what they say, he said, did they make it? He's like, what made it did not live very long. Like they came back as something that was not human. So, it's scary stuff. I'm glad to know that I will not live long enough to see it.
But that's the thing. And it literally, like I said in the beginning, the reasons that freak you out and make you not want to think about it are the exact reasons why
You find it beautiful.
Yeah. Because it is. It's because of that connection to philosophy, and that it opens up all these other possibilities for the nature of our reality. And I say possibilities when in truth, it really just means that's the way it is, and we've just never been aware of it before.
I understand that. I get that. But like I said just now, let that be someone else's discovery, because I definitely do not want that on my plate. Let that happen in someone else's world. I don't want to think about it, because it is, I think it comes across with the religion aspect of it. That's why people go to religion so easily, because when you think about the universe as a huge, what it is, it's scary to understand that there's so much out there that we don't know yet.
Right.
And so, and even stuff that we have no control over, you know? And so people, I'm not saying they flock to religion for this reason, but it's a comfort that people find in religion, that there's some kind of cosmic order to things.
Yeah.
And that things are as they were designed to be, not we're just basically floating on this planet in this universe and random stuff is going to hit us. You know, like that Albert Einstein thing, that the certainty is better to know and live in than the probability of something, you know? And I think that's why people kind of, does that make sense? Like that, why people find comfort in religion?
Yeah.
Okay. Now look, and we can go on a tirade all day long with this one, but you know, and then the man gets involved in religion, then it gets all effed up. So, you know, it gets twisted into what it is. But at its nature, spirituality is a beautiful thing. Do you know what I mean? Like, it is. And I'm a spiritual person, and I do find comfort that there's things beyond, I almost said sight beyond sight. But I do find comfort in that kind of stuff, that there is something maybe bigger than us, and there is an order to things.
Yeah.
But the universe is going to reveal its secrets one day. It's like I told you earlier. I told Thomas, I said, the only time we're ever going to find out is when we die. And then that's when the universe's secrets hopefully are revealed to us. I'll be riding that wave.
So, you know, like Michael said, all those things I find really fascinating. All the theoretical possibilities and probabilities of things that are out there that we have no knowledge of, and can, well, that's just like, we didn't even talk about the fact that string theory also opens up the need for more than just 3 physical dimensions.
Yeah.
You know, essentially what that boils down to, though, the simplest explanation for that is not like another dimension, like another plane of existence, but other dimensions in terms of like beyond height, width, depth, but
like a 5th dimension as opposed to
10.
No, see, here you go. Let me get my aspirin out real fast, because I'm not going to be able to even comprehend this one.
But basically, so string theory says that all these extra dimensions exist all around us. We're just not aware of them because they are so tiny that we can't really perceive them. And it's just like the I think the same documentary that you watched did this, but it's just like if you look at a power line that's 100 feet away, that looks like just a straight line. It doesn't look from that far away like it has any depth to it.
Right.
But if you look at it up close, it's actually got a circumference, and it's large enough that, you know, an ant can actually walk all the way around on. And so they say essentially that's where all these other dimensions exist, is on the quantum level, where they are essentially folded up on themselves on this tiny level that we just can't see them, but that's where they exist. And that's the dimensions through which things at the quantum level can travel.
Right. Okay. And I can see that, because we do know that there are things that we can't fathom. Okay. So like dogs smell so much more than us.
Yeah.
Hear so much more than us. Don't see as much as us.
You
know, but that's because our limitations as humans don't allow us to see that. So I'm on that roller coaster with you. I can see that.
The dimensions? Yeah.
Yes, I can see that. I think I can fathom that.
Okay. Good. So we talked about dogs, but what about cats?
Well, I don't want to talk about that because they can see things that they should not be seeing.
Well, so can dogs, but no, I'm talking about one very special cat.
Oh,
Schrodinger's cat.
Yeah. Did I say Schroeder's like the
Schroeder? Yeah.
the guy from Peanuts?
No, not the one Lucy is in love with, but Schrodinger. So, and that's not even really so much a string theory thought experiment. That's more just a quantum physics thought experiment.
Yeah.
But it goes back to, so we didn't really talk about superposition, did we?
Nope.
So another thought experiment that examines some of the stuff that Michael was talking about earlier is the experiment known as Schrodinger's cat. And essentially it looks at superposition superposition and the Heisenberg principle.
Mm-hmm.
Okay, so in the thought experiment, a cat is sealed in a box along with a vial of poison and a radioactive element that if the radioactive element decays, it is going to release a hammer that's going to break the vial of poison and kill the cat.
Mm-hmm.
Okay, so with superposition in string theory, at the subatomic level, at the quantum level, you have particles that are going to exist essentially in two states until they are observed.
Mm-hmm.
So either going to decay or not going to decay are the two possible states that it can be in. And so essentially you don't know whether it is going to decay or not going to decay until you open the box and see if it did and killed the cat. So until that box is opened and a conscious observer sees the results of the experiment, both states exist at the same time, which means that not only is that atom in the state of going to decay and not going to decay at the same time, but also the cat exists in alive and dead states at the same time until you open the box and observe which of the states occurs.
So by not having any view inside the box, you don't know if it's dead or alive.
Right.
So in your mind, it's either dead or alive. It like you said, it exists in a state of death or living.
It exists in both.
No.
At the same time.
No.
Because of superposition.
No.
Well, and that's what Schrodinger said. Schrodinger created this thought experiment as a means of saying that the theory was wrong. But nevertheless,
that cat's alive until I open the box and it degrades and it kills it. Or if it's in the box for 15 years, I know it's going to be dead eventually.
But according to the experiment, you don't need to wait 15 years or anything because it's both alive and dead at the same time.
Well, what if you never open the box? And 20 years from now, the cat's obviously dead. Is he still alive, though?
No, because at that point, you've taken out the factor of the radioactive decay being the point of decision.
Okay.
Yeah.
Because time became the decision then.
Right.
Okay. It's like if a bear poops in the woods, does he really poop? And if no one's around to hear a bear fart in the woods, does it really fart?
Well, no, I mean, but what's the answer to not the bear, but the old question of if a tree falls in the woods, does it make a sound?
Yeah, because the sound's going to happen no matter what.
Nope.
Because we live in a world of
nope.
Well,
It creates sound. It creates sound waves. But what is one of the requirements for sound to be produced?
You have to have you have to have a receiver.
A receiver, exactly. So it creates sound waves, but not sound.
That's semantics.
No, it's not.
Yes, it is.
No, it's not.
Okay.
Look it up.
Nope. Nope.
So yeah, without that receiver, no sound was made. All right. But yeah, so string theory is a fascinating peek into this exotic realm of potentiality that may indeed be exactly how the universe exists all around us, and we just can't tell because we can't observe it. So what are your final thoughts on string theory?
I'm glad it's just a theory. I'm going to tell you what, man. I'm glad to know that I can appreciate it, but still kind of be fearful of it. I was terrified of going into this topic with you because I was terrified I would not be able to understand it. And like I said, it was very intimidating, just the words and the advanced knowledge of it.
Yeah.
But I have a better appreciation for it now, I guess. I'm still kind of boggled out that this whole teleportation thing is like not me. But like I said earlier, I'm glad it's not going to happen in my lifetime. I mean, I'm glad we did this topic.
Good. I'm glad you...
I'm open-minded. I am.
I'm glad you've come around to that
No, I didn't say
conclusion.
all that. I said I'm okay with doing this topic.
No, that's that you were glad that we did this topic.
Okay.
That's yeah, that's what I'm talking about. So obviously, this has fascinated me for many years, ever since I first learned about it. And for me, it goes back to really the religious aspect of it that you were talking about earlier. Because, and now granted, one of our other topics for a future episode that I also came up with, one of the first ones on my list, was science versus religion. But for me, string theory it's not something that intimidates me in terms of like, how can that possibly be or anything like that. It's simply another
Affirmation.
kind of it's another little wink, if you will, at there's more to it than meets the eye.
Mm-hmm.
And there's more to it than what you could possibly understand.
Mm-hmm.
And that's really how I think about the world and the science that explains the world and nature and the universe, because ultimately I simply believe that science is just, or what we observe as science is just the machinations through which God works.
Yeah.
And so, I find it no less miraculous,
Yeah.
knowing that this is how something works than if it were, a mysterious, just it just is because that happened because God made it so.
Yeah. No, before we get into that topic, though, I need to read a book
Okay.
to kind of help me with that.
A specific book, or do you just mean?
No, there's a book that I have been meaning to read by Kenneth Miller, who's a theologian, but also a biologist.
Oh, okay.
And in the book, it's evolution.
Mm-hmm.
It takes on evolution. It's finding Darwin's God.
Mm-hmm.
And we're in Darwin now. And, when you look at Darwin as a man, not as the scientist, I guess,
Mm-hmm.
very spiritual, very religious, inner turmoil of his observations.
Yeah.
But Kenneth Miller in this book basically not only kind of doesn't, I guess, settle the debate between evolution and religion,
Mm-hmm.
but kind of marries the two.
Yeah.
And actually uses, I guess by the end of the book, from what I understand, is that evolution is actually a strong case for the existence of God.
Yeah.
And I think that's kind of going along what you're saying. Like, it brings
Yeah.
you closer to your religion,
Yeah.
your spirituality and God, in thinking about these bigger topics and things that science is evidence of that.
Yeah.
Yeah.
Yeah, exactly. Okay. And so, that aspect of string theory has always given me comfort in that sense. But then also there's a certain beauty in the thought of everything in the universe not being made up of something physical, but out of being made up of something energetic, being made up of something of a piece. I don't know that you could say a piece of energy, but a form of energy that is a vibrating string.
Yeah.
And, when, we talked about Michio Kaku a lot in this episode, and, every time he talks about string theory in a documentary, he talks about a symphony, and he talks about all the different frequencies at which these strings vibrate, creating, these notes and then these chords and these harmonies and culminating into the symphony that is the universe of all these vibrating strings. And so I find a lot of beauty in that aspect of it and thinking of it in that sense. So, of course, you give me something like that the whole universe is essentially a symphony.
Mm-hmm.
Heck yeah, I'm going to be obsessed with it.
Yeah.
All right. Ready for trivia?
Yep.
All right. Well, in honor of tonight's topic, I definitely want to go with science and nature.
All right. I don't know if I'll be able to see. Not because I can't see, but because the lighting in this studio is horrific.
Well, if you would ever help me change the ceiling fan like I asked you to over the summer.
You have that light over there. Turn that light on.
That one little light is not going to help us.
Well, this one little light on my phone will.
This little light of mine.
It's barely shining. Okay. What is the common name for the fluid expelled from the body by the process of Lacrimation.
Milk?
Nope.
Lacrimation?
Yeah, Lacrimation. Had to make sure that wasn't an N. Yeah.
Lacrimation.
Yeah.
Expelled by the body.
What kind of fluid is expelled by the body?
Urine?
No. That's urination.
Sweat.
No.
What is it then?
Tears.
Okay.
I almost said what you and Thomas did watching Wicked for the 18th time.
Oh, shut up.
Cried each time. Like you didn't know what was going to happen.
I didn't cry the 18th time.
All right,
I
this is
wasn't
an easy
invited past the second.
You only saw it twice?
Yeah.
Oh.
Like I
I saw
said,
it
I
4
wasn't
times.
invited those other times.
Oh, that's true. I saw it 4 times.
I know.
It's out on DVD.
And on streaming.
Yeah, but the DVD's better.
I know, but I don't even use a DVD player anymore.
Well, that's true.
I don't have my DVD set up.
Okay. This is easy. What element with the symbol I is found in seawater and has the name based on the Greek for violet?
Iodine?
Yes. What company produces the iPod? Well, how old is this? book?
What?
What company produces the iPod? I'm not kidding. iPod.
Apple.
Yeah. What was the
Pear.
name? What was the name of What was the name of Earth's first artificial satellite?
Earth's first artificial satellite?
Yes.
Sputnik? 1?
Yeah, there you go. I'm assuming there was more than one. So.
There was.
Okay. What does an entomologist study?
Entomologist? Entomologist. Bugs.
What part of the space shuttle's power systems are referred to as SRBs? This is so easy.
Solid rocket booster.
What? The space shuttle's dead for like 15 years now.
It's an old book. I'm sorry.
Give me this one right here. The one on the previous page.
That you see all the answers to right there?
I'm memorizing them. Yeah, that one.
Oh, was that the last one?
Oh, I don't know.
The question
Oh,
was-
yeah, that's the last one. Yeah, I know.
It's
That's the last
okay.
page. Yeah, that's the last question.
Let me turn to a very different page, not the one that he asked for.
Rude.
Ooh, that might be a good one. Again, judging by the answers. Yeah, you should know most of the other things. Number 1, what can be found under the hood of a car to visually measure the oil level?
Oh, a dipstick.
Yeah. Number 2, what animal produces cashmere wool?
A sheep?
No.
Cashmere.
Mm-hmm.
Oh, it's a spider?
No. You were closer the first time.
A goat?
Yes.
Ew.
What do you mean? Ew.
Next time I see someone in a cashmere store, I go, bah, bah.
That's a sheep, not a goat.
Oh.
All right. Number 3. What gas makes up approximately 74% of the sun's mass?
Hydrogen.
Yes. Do you know what mostly makes up the rest of it?
I'm assuming helium.
Yeah. That's not on here. That's just fun fact. All right.
That is Brandon Shoemaker's flash fact of the day.
Flash fact. I like that. What does a coleopterous study?
Can I see it?
Yes.
Am I going to get it?
No.
The colon.
No.
No, what is it?
Beetles.
Yeah, I wouldn't have got that.
I'll be honest. When I saw beetles on the other side, I didn't pay attention to the spelling, and I thought it was going to be referring to the
musical group.
Yeah. I thought they meant John, Paul, George, and Ringo. All right. Number 5. What type of dinosaur snatched the man off the toilet in the movie Jurassic Park?
The T-Rex?
Yeah.
Do you know who the man was?
Wasn't it, what's his name? Newman from Seinfeld?
Yeah.
Yeah. All right. And number 6. What is your shirt made from if the fiber was produced by the
What's up with these textile questions?
Gossypium?
Pick a different question from another page.
What is, we can do this one. What is your shirt made from if the fiber was produced by the Gossypium shrub?
From a plant?
Oh. Mm-hmm.
Bamboo? What?
The Gossypium shrub.
I don't know. Cotton.
Yeah.
Okay.
Yeah, cotton.
Weird.
I know, but kind of cool, isn't it?
No, they don't sell Gossypium shrub shirts. They sell cotton shirts.
Right, because cotton grows
you sleep
from
in Gossypium plant. Well, that's the flower of the plant, I guess, right?
I don't really know. I don't. It grows out of the flower, I think.
Well, it's got seeds in it. The cotton has the cotton seeds in it, correct?
Yeah.
Then that's the. I don't know.
Yeah, I don't know.
It's plant poop.
We're wearing plant poop.
Yep. And we sleep in plant poop.
Yep.
Unless you're an Egyptian. Then you sleep in what?
What?
What's Egyptian cotton made out of? Silk?
No.
What?
Egyptian cotton is still.
Oh, Egyptian cotton. It's okay. Yeah,
still cotton.
Never mind.
Okay, but if you sleep on silk sheets, there you go. Then you're
Sleeping on spider poop.
Yeah. Is it really poop though?
No.
Yeah.
Well, no, it's not. It's just.
It's still something that comes out of them.
No, it's they make a protein.
Okay.
It's just what they.
It's just their silk, their webbing, right?
Yeah.
Yeah.
That's all it is.
Okay. All right. Well, after all those random facts that we added on at the end, that most of which I'll have to take out,
that you'll never hear because it's neither here nor there.
All right. Well, that does it for this week's episode of From Art to Atoms.
The Ultimate Curiosity Show, guys.
Thanks so much for joining us this week on one of my favorite topics, and we hope you join us again next week for another interesting idea.
Yeah. Have a good one.
Bye.
You've been listening to From Art to Atoms, The Ultimate Curiosity Show, episode number 22. Your hosts are Brandon Shoemaker and myself, Michael Fols. The show is produced by Brandon Shoemaker and is available on Apple Podcast, Spotify, Amazon Music, iHeartRadio, or wherever you get your podcast. Be sure to subscribe to the show to stay up to date on all of our latest episodes and news. If you have any questions, feedback, or suggested topics you'd like for us to dive into, don't hesitate to reach out. You can email us at FromArtToAtoms@gmail.com. We would love to hear from our listeners, and we value your input. Don't forget to follow us on social media to stay updated on upcoming episodes and behind-the-scenes content. You can always find us on Instagram and YouTube at From Art to Atoms. If you enjoyed today's episode, please take a moment to rate and review us on your favorite podcast platform. All of your support helps us reach even more interesting minds like yours. Thanks for tuning in, and as always, stay curious.